Galaxies, vast islands of stars, gas, and dark matter, may seem eternal and serene, but in the grand timeline of the universe, they are destined to collide in spectacularly violent events. These cosmic crashes aren't rare anomalies, but fundamental parts of our universe's evolution, shaping the very fabric of what we see through our telescopes today. In the vast emptiness of space, it might seem strange that galaxies would ever meet. After all, the universe is expanding, constantly growing larger with each passing moment. Yet within this expansion lies a beautiful contradiction. While space itself stretches, the gravitational bonds between nearby galaxies can be strong enough to overcome this cosmic drift, pulling these giant star systems toward one another in a dance that spans billions of years. Gravity, the silent architect of our cosmos, orchestrates these encounters. The same force that keeps your feet planted on Earth works across unimaginable distances, tugging at galaxies with gentle but persistent hands. A galaxy's immense gravitational field reaches out far beyond its visible borders, influenced by not just its stars, but the mysterious dark matter that makes up over 80% of its mass. This invisible substance creates a gravitational web that can trap passing galaxies, drawing them into slow-motion collisions that unfold over hundreds of millions of years. When galaxies begin their approach, they don't simply crash head-on like cars in an accident. Instead, they perform an elaborate gravitational dance, circling and tugging at each other's edges. Stars and gas clouds are pulled into long, luminous bridges between the galaxies. These tidal tails, as astronomers call them, stretch like cosmic ribbons across millions of light years, creating some of the most beautiful structures we can observe in the universe. The violence of these encounters is both destructive and creative. As galaxies surge, massive clouds of hydrogen gas collide and compress, triggering the birth of millions of new stars in brilliant bursts of creation. These starburst regions shine with the light of young hot stars, often outshining their entire host galaxies. What looks like destruction from afar is actually a tremendous surge of new stellar life. Perhaps most fascinating is how these collisions transform the galaxies themselves. Elegant spiral galaxies with their characteristic pinwheel shapes can be warped beyond recognition, their delicate structures torn apart by gravitational forces. After billions of years of interaction, what often remains is an entirely new type of galaxy, a massive elliptical galaxy with little of the original structure remaining, but containing the combined stars of both original systems. Our own Milky Way galaxy bears the scars of past collisions. The halo of stars surrounding our galaxy contains the remnants of smaller galaxies that were cannibalized by our larger spiral. Even now, several dwarf galaxies are being slowly consumed by our Milky Way, their stars gradually absorbed into our galactic home. And the story isn't over. In roughly 4 billion years, our Milky Way is destined for its own major collision with our nearest large neighbor, the Andromeda Galaxy. This future merger, already in its earliest stages as Andromeda moves toward us at over 100 kilometers per hour, will completely reshape our cosmic neighborhood and give our distant descendants an entirely different night sky, if humanity still exists to witness it. Tendrils of stars embracing one another in gravitational arms and eventually merging into a single entity. The universe we observe today is filled with evidence of these violent encounters. Nearly every large galaxy shows signs of past mergers, unusual streams of stars, shells of gas ejected during ancient collisions, or strangely warped disks that haven't quite settled after a cosmic disturbance. In the most extreme cases, we can observe galaxies actively colliding, frozen in various stages of their gravitational dance by the finite speed of light, which delivers these ancient images to our telescopes millions or even billions of years after the events took place. In the core of each large galaxy lies another player in this cosmic drama, a supermassive black hole with the mass of millions or billions of suns. When galaxies collide, these behemoths begin their own slow journey toward each other, eventually merging in events so powerful they send ripples through the very fabric of space-time. These gravitational waves, first predicted by Einstein, and now directly detected by our instruments, carry the energy of these monumental events across the cosmos. The Hubble Space Telescope, along with newer observatories like the James Webb Space Telescope, has captured breathtaking images of galaxies caught in various stages of collision. The antennae Galaxies, located about 70 million light-years from Earth, show spectacular tidal tails stretching far into intergalactic space. The system known as ARP 220, with its bridge of stars connecting two spiral galaxies, reveals the early stages of a cosmic merger. And the strangely shaped Cartwheel Galaxy, resembling a wagon wheel floating in space, was likely formed when a smaller galaxy punched through the center of a larger one, creating a ripple effect like a stone dropped in a cosmic pond. These collisions don't just reshape individual galaxies, they help form the larger structures we see in the universe. Galaxies tend to cluster together in groups and clusters, which themselves form even larger structures called superclusters. These superclusters form the largest structures in the cosmos, vast walls and filaments of galaxies surrounding relatively empty voids, creating what astronomers call the cosmic web. This web-like arrangement of matter on the largest scales is partly the result of countless galactic mergers throughout cosmic history, as gravity has worked to clump matter together against the expanding backdrop of space. The story of galactic collisions is also intimately connected to the formation of elements necessary for life. While the lightest elements, hydrogen and helium, were formed in the first few minutes after the Big Bang, heavier elements are forged in the hearts of stars. When galaxies collide and trigger new waves of star formation, they accelerate the production of these heavier elements. As massive stars live fast and die young in spectacular supernova explosions, they seed their surroundings with carbon, oxygen, iron, and other elements essential for planets and life as we know it. In a very real sense, the violent history of galactic collisions help create the conditions necessary for our existence. While galactic collisions sound catastrophically violent, and on a cosmic scale, they certainly are, it's important to understand that the vast distances between stars mean that direct stellar collisions are extremely rare during these events. If our Milky Way and Andromeda galaxies merge as expected, the Sun and Solar System will likely be thrown into a different orbit around the new galactic center, but the chances of our Sun physically colliding with another star are vanishingly small. The space between stars is simply too vast. If our Sun were the size of a grape, the nearest star would be about 1,000 kilometers away. What makes these collisions so fascinating is the contradiction they represent. Events of unimaginable violence that unfold with balletic grace across billions of years, simultaneously destroying existing structures while seeding the creation of new stars and potentially new worlds. They remind us that the universe is not static, but dynamic, constantly evolving through cycles of creation and destruction that operate on timescales far beyond human experience. As we observe distant galaxies caught in various stages of collision, we're also looking back in time. The further we peer into space, the further back in time we see, due to light's finite speed. This cosmic time machine allows astronomers to study how galaxy mergers were different in the early universe compared to more recent cosmic history. We've discovered that galactic collisions were much more common billions of years ago, when the universe was smaller and galaxies were closer together. This higher collision rate helped build up the large galaxies we see today, including our own Milky Way. The tools we use to study these cosmic crashes have evolved dramatically over the decades. Modern astronomers combine observations across the electromagnetic spectrum, from radio waves to gamma rays, with sophisticated computer simulations that can model the complex gravitational interactions between billions of stars, vast clouds of gas, and the invisible dark matter that forms each galaxy's skeleton. These simulations allow us to wind cosmic time backward and forward, reconstructing past collisions and predicting future ones with remarkable accuracy. To understand why galaxies collide, we must first understand how they form and move. The story of galactic collisions begins with the birth of the galaxies themselves in the early days of our universe. To fully appreciate the cosmic ballet of colliding galaxies, we must journey back to the universe's infancy, when the first galaxies began to form. Roughly 13 billion years ago, just a few 100 million years after the Big Bang, the universe was a very different place. The initial expansion had cooled the cosmos enough for matter to begin clumping together under the influence of gravity. But there were no stars, no planets, and certainly no galaxies as we know them today. In those early cosmic moments, the universe was filled with a nearly uniform fog of hydrogen and helium gas, with tiny fluctuations in density. Quantum ripples stretched to cosmic proportions by the rapid inflation that followed the Big Bang. These slight variations might seem insignificant, but they contain the seeds of everything we see today. In regions where the density was just slightly higher than average, gravity had a stronger pull. Over time, these areas drew in more and more matter, growing steadily denser in a self-reinforcing cycle. Dark matter, the mysterious substance that neither emits nor absorbs light but interacts through gravity, played a crucial role in this process. Making up roughly 85% of all matter in the universe, dark matter formed massive halos that served as gravitational anchors, pulling in ordinary matter to create the first galactic structures. Think of these dark matter halos as invisible scaffolding, cosmic frameworks upon which the visible galaxies would eventually be built. As gas clouds fell into these gravitational wells, they began to heat up and compress. When the density and temperature reached critical thresholds, nuclear fusion ignited, and the first stars burst into brilliance, illuminating the cosmic darkness for the first time. These earlier stars were nothing like our Sun. They were giants, hundreds of times more massive, burning hot and fierce with lifespans measured in millions rather than billions of years. Their powerful radiation began to ionize the surrounding gas, creating bubbles of transparent space in the cosmic fog. These first-generation stars were also cosmic factories, forging heavier elements in their cores, and then scattering them across space when they died in spectacular supernova explosions. Each generation of stars enriched the universe with more of these heavier elements: carbon, oxygen, silicon, iron, the building blocks that would eventually form planets, and much later, living things. This process of stellar birth, life and death created the rich mixture of elements that makes our complex universe possible. Gradually, these early star clusters began to merge and grow, forming the first proto-galaxies, chaotic, irregularly shaped collections of stars and gas that bore little resemblance to the majestic spirals and ellipticals we see today. These primordial galaxies were much smaller than modern ones, perhaps just 1/10 the size of our Milky Way. But they were destined to grow through a process of hierarchical assembly, smaller galaxies merging to form larger ones in a cosmic version of survival of the fittest. As the universe continued to expand and evolve, 3 main types of galaxies emerged, each with distinct characteristics that we can observe even today. Spiral galaxies, like our own Milky Way and the neighboring Andromeda, are characterized by flat, rotating disks with elegant spiral arms winding outward from a central bulge. These spiral arms aren't physical structures, but density waves, regions where stars and gas clouds bunch together temporarily as they orbit the galactic center, much like cars slowing down in a traffic jam before moving on. Elliptical galaxies, by contrast, lack this organized structure. They appear as smooth, featureless ellipsoids of stars with minimal gas and dust, and little ongoing star formation. These cosmic giants can contain trillions of stars and often dominate the centers of galaxy clusters. The third major type, irregular galaxies, have no definable shape at all. They are cosmic oddballs, often distorted by gravitational interactions with neighboring galaxies or formed through recent mergers. But how do galaxies move through the cosmos? Unlike stars orbiting within a galaxy, galaxies themselves don't orbit around a central point. Instead, they move through space under the influence of gravity from neighboring galaxies and the large-scale distribution of dark matter. This movement isn't random. It follows the invisible contours of what astronomers call the cosmic web, a vast network of dark matter filaments that stretches across the observable universe. Imagine the universe as a cosmic landscape, with hills and valleys formed by concentrations of mass, Galaxies, like cosmic raindrops, tend to flow downhill toward the gravitational valleys where they collect into groups and clusters. The Milky Way, for example, is part of the local group, a collection of over 50 galaxies dominated by ourselves and Andromeda. This local group, in turn, is being pulled toward a much larger concentration of galaxies called the Virgo cluster, which contains thousands of galaxies. On an even grander scale, the Virgo cluster is part of an enormous supercluster of galaxies that astronomers have named Laniakea, Hawaiian for immense heaven. This supercluster spans more than 500 million light-years and contains approximately 100,000 galaxies, all flowing along dark matter filaments toward a gravitational focal point nicknamed the Great Attractor. Such is the scale of motion in our universe. Individual galaxies, groups, clusters, and superclusters, all flowing through space like cosmic rivers converging into gravitational oceans. The speeds at which galaxies move can be staggering. Our Milky Way, for instance, is hurtling through space at approximately 600 kilometers per second, relative to the cosmic microwave background, the afterglow of the Big Bang that serves as a reference frame for cosmic motion. Some galaxies move even faster, particularly those falling into massive galaxy clusters, where they can reach speeds of thousands of kilometers per second. These motions aren't just academic curiosities, they determine which galaxies will eventually meet and merge. When two galaxies pass close enough to each other, their mutual gravitational attraction can overcome their relative motion, causing them to enter into a bound orbit. Like a cosmic version of two ice skaters grabbing each other's hands and spinning together, these galaxies begin a gravitational rotating in the same direction, might merge relatively smoothly, while those with opposing rotations can produce more chaotic results. Dark matter, though invisible, plays a starring role in this cosmic drama. The halo of dark matter surrounding each galaxy extends far beyond the visible stars, creating gravitational effects that can be felt millions of light-years away. These extended halos interact long before the visible portions of galaxies make contact, beginning the merger process in darkness, like ghostly hands reaching across space to draw galaxies together. Modern astronomical observations have revealed that galaxy mergers were much more common in the early universe than they are today. Billions of years ago, when the universe was younger and more compact, galaxies were packed closer together and moved through space at lower relative speeds, making gravitational captures more likely. High-resolution images from space telescopes like Hubble and James Webb have allowed astronomers to peer deep into cosmic history, revealing a universe teeming with galactic interactions and mergers. These ancient collisions weren't just common, they were essential to building the universe we see today. Without them, large galaxies like our Milky Way could never have formed. Each merger added more stars, more gas, and more dark matter to the growing galaxies, while also triggering bursts of new star formation as gas clouds collided and compressed. Our own galaxy likely experienced its last major merger more than 10 billion years ago, though it has continued to cannibalize smaller dwarf galaxies throughout its history. The evidence of past mergers is written in the stars themselves. Astronomers studying the motion and chemical composition of stars in our galaxy have identified structures called stellar streams, ribbons of stars all moving together on similar orbits with similar chemical fingerprints. These streams are the stretched-out remains of dwarf galaxies that were pulled apart by the Milky Way's gravitational forces, their stars now incorporated into our galactic home, while still maintaining a ghostly record of their original identity. Even now, we can observe this process in action. The Sagittarius dwarf spheroidal galaxy is currently being torn apart by interaction with the Milky Way, its stars forming a long stream that wraps around our galaxy multiple times. The large and small Magellanic Clouds, irregular dwarf galaxies visible to the naked eye from the southern hemisphere, are also locked in a gravitational dance with our galaxy. Simulations suggest they will eventually merge with the Milky Way in the distant future. But the most significant merger in our cosmic neighborhood is yet to come. The Andromeda Galaxy, our largest neighbor at 2.5 million light-years away, is moving toward the Milky Way at roughly 110 kilometers per second. This motion will bring the two spiral galaxies together in approximately 4.5 billion years. When they meet, these majestic spirals will engage in a cosmic dance lasting hundreds of millions of years, eventually forming a giant elliptical galaxy that astronomers have already named Milkomeda. As galaxies move through the cosmos on their predestined paths, they carry with them the essential ingredients for worlds and potentially for life itself. The stars, planets, gas and dust that make up these vast cosmic cities are in constant motion, rotating around galactic centers, flowing along spiral arms, and ultimately carrying entire galaxies toward inevitable encounters with their neighbors. In the grand cosmic timeline, these collisions aren't disasters, but essential chapters in the ongoing story of universal evolution. As galaxies drift inexorably closer to one another, they begin to feel each other's gravitational influence across the vast gulfs of space. And when this attraction becomes strong enough, the stage is set for one of the most spectacular events in the cosmos, a galactic collision of truly cosmic proportions. In the vast theatre of the cosmos, gravity is both playwright and director, authoring and orchestrating the most spectacular shows in the universe. The collision of galaxies, those immense cities of stars, represents gravity's grandest production, played out across billions of years and trillions of kilometers of space. To understand why these cosmic titans crash together, we must first fully appreciate gravity's subtle but inexorable influence. Gravity, as described by Einstein's general theory of relativity, isn't truly a force in the conventional sense. Rather, it's a warping of space-time itself. Massive objects like stars and galaxies create depressions in the fabric of the universe, rather like heavy balls placed on a stretched rubber sheet. Other objects then follow the curves and contours of this warped space-time, which we experience as gravitational attraction. The more massive an object, the deeper the depression it creates, and the stronger its gravitational pull becomes. Galaxies are among the most massive single structures in our universe. A typical spiral galaxy like our Milky Way contains hundreds of billions of stars, vast clouds of gas and dust, and an even more massive halo of dark matter extending far beyond the visible disk. Altogether, the Milky Way has a mass equivalent to roughly 1 trillion suns. Such enormous concentrations of matter create significant distortions in space-time that can be felt across millions of light years. When two galaxies pass within a certain critical distance of each other, their gravitational influence begins an intricate dance that can last for billions of years. Initially, each galaxy feels a slight tug toward the other, a gentle gravitational embrace that begins to alter their paths through space. If the galaxies are moving slowly enough relative to each other, this mutual attraction can overcome their relative motion, causing them to enter a bound orbit around a common center of mass, rather like a cosmic version of two-figure skaters clasping hands. What's remarkable about this gravitational interaction is that it begins long before the visible portions of the galaxies come anywhere near each other. The extended dark matter halos surrounding each galaxy, invisible to our telescopes but detectable through their gravitational effects, make first contact millions of years before stars or gas clouds from the two galaxies meet. These massive halos act like invisible tendrils, reaching across space to draw galaxies together in an embrace that will ultimately prove inescapable. The concept of gravitational capture is central to understanding why galaxies collide. For two galaxies to merge, their relative velocity must be low enough that their mutual gravitational attraction can overcome their motion and bind them together. This is more likely to happen in regions of space where multiple galaxies have already clustered together, creating a stronger combined gravitational field. These regions, appropriately named galaxy groups and galaxy clusters, are cosmic hotspots for galactic mergers. Our own local group, a collection of more than 50 galaxies dominated by the Milky Way and Andromeda, provides a perfect example of this clustering effect. The galaxies within our local group are bound together by gravity, slowly moving closer to one another over cosmic time. Smaller members of the group, like the Large and Small Magellanic Clouds, are already being torn apart by the Milky Way's gravitational pull, their stars and gas gradually being incorporated into our galaxy. On a larger scale, galaxy clusters represent even denser environments where collisions are commonplace. The Virgo cluster, the nearest major galaxy cluster to Earth at approximately 54 million light-years away, contains about 1,500 galaxies packed into a volume just 20 million light-years across. In such crowded neighborhoods, galaxies frequently pass close enough to one another for gravitational capture to occur. Computer simulations suggest that nearly every large galaxy in a dense cluster has experienced at least one major merger in its lifetime. What makes these cosmic collisions particularly fascinating is their slow-motion nature. Despite involving masses equivalent to trillions of suns moving at hundreds of kilometers per second, galactic mergers unfold over timescales that stretch human comprehension. A typical collision between two large galaxies might take 500 million years to complete, more than 3 times longer than mammals have existed on Earth. If we could somehow watch a galactic collision at normal speed, it would appear completely frozen, with changes detectable only over millions of years. This extreme timescale creates a unique observational opportunity for astronomers, because light travels at a finite speed. When we look at distant galaxies, we're seeing them as they were millions or billions of years ago. By observing galaxies at different distances, astronomers can effectively see different stages of the collision process frozen in time, creating a cosmic collision catalogue that spans billions of years of universal history. Computer simulations have become essential tools for understanding these extended processes. Modern astrophysicists use supercomputers to model the gravitational interactions between millions or even billions of particles, representing stars, gas clouds, and dark matter. These simulations can compress hundreds of millions of years into minutes of computation time, allowing scientists to watch cosmic collisions unfold from beginning to end and to test their theories against actual observations. These simulations have revealed the enormous variety of possible collision scenarios. When two galaxies of similar size collide, the outcome depends greatly on their relative trajectories and orientations. Galaxies that meet head-on experience more dramatic disruption than those that graze each other's edges. Spiral galaxies approaching with their disks aligned tend to preserve more of their original structure than those meeting at odd angles, and the relative speed of the encounter plays a crucial role. Faster collisions may result in galaxies passing through each other and separating again, while slower encounters more often lead to complete mergers. Regardless of the specific scenario, gravity ensures that these encounters aren't one-time events. Even when two galaxies pass through each other without immediately merging, their mutual gravitational attraction typically causes them to reverse course and fall back toward each other for a second encounter. This cosmic dance can repeat multiple times, with each pass stripping away more stars and gas, until the two galaxies have lost enough energy through friction and gravitational interactions to merge completely. The role of dark matter in these collisions cannot be overstated. Making up roughly 85% of the matter in most galaxies, dark matter dominates the gravitational interactions between them. However, unlike stars and gas clouds, dark matter doesn't collide or interact directly with other matter. It passes right through, affected only by gravity. This creates a fascinating dynamic during galaxy collisions, where the visible and invisible components behave quite differently. The dark matter halos may pass through each other with minimal disruption, while the visible matter experiences significant compression, shock waves, and tidal disruption. Perhaps the most dramatic evidence of dark matter's unique properties comes from observations of the Bullet cluster, a system where two galaxy clusters collided approximately 150 million years ago. As the clusters passed through each other, the hot gas in each cluster slowed down due to electromagnetic interactions, creating a distinctive pattern visible in X-ray observations. But gravitational lensing measurements, which detect how light from distant sources is bent by mass, showed that most of the mass kept moving, separating from the visible gas. This separation provided compelling evidence for dark matter's existence and its non-interacting nature. For galaxies in less dense environments, like those found in the vast cosmic voids between galaxy clusters, collisions are much rarer. These isolated galaxies may drift through space for billions of years without experiencing a significant gravitational interaction. Even in these cases, however, the large-scale structure of the universe, the cosmic web of dark matter filaments connecting galaxy clusters, gradually shepherds galaxies toward denser regions where mergers become more likely. The inevitable collision between our Milky Way and the Andromeda Galaxy illustrates many of these principles. Currently separated by about 2.5 million light-years, these two spiral giants are moving toward each other at around 110 kilometers per second. Despite the vast distance between them, their combined mass of approximately 2 trillion suns creates enough gravitational attraction to overcome the universe's expansion in our local region of space. Computer simulations suggest that after their first pass through each other, approximately 4.5 billion years from now, they will make several more passes before merging completely into a giant elliptical galaxy. What makes this future collision particularly interesting is that it will occur when our Sun is nearing the end of its life as a main sequence star. As our star begins to expand into a red giant, the night sky on Earth, if Earth still exists, would be transformed by the approach of Andromeda, which would appear as a vast spiral structure several times larger than our full moon. Later generations might witness spectacular starbursts as gas clouds collide, igniting waves of new star formation across the merging galaxies. The clustering of galaxies plays a crucial role in determining collision rates throughout cosmic history. In the early universe, when everything was closer together, mergers were much more common. As the universe expanded, the average distance between galaxies increased, making random encounters less likely. Today, significant mergers primarily occur within galaxy groups and clusters, where gravitational attraction has kept galaxies bound together against the cosmic expansion. This clustering effect creates a hierarchy of structures in our universe. Individual stars gather into galaxies, galaxies form groups and clusters arrange themselves into superclusters along the filaments of the cosmic web. At each level, gravity works to gather matter into ever larger concentrations, counteracting the universe's overall expansion. The collision and merger of galaxies represents one crucial step in this hierarchical assembly process, the means by which small galaxies from the early universe have grown into the massive systems we see today. Observations of distant galaxies have shown that collision rates were much higher in the past. When we look at galaxies 8 to 10 billion light-years away, we're seeing them as they were 8 to 10 billion years ago, when the universe was less than half its current age. These observations reveal a cosmic landscape teeming with distorted, interacting galaxies, evidence of a much more dynamic and chaotic period in our universe's history. By contrast, the present-day universe shows a lower rate of major mergers, though minor mergers with dwarf galaxies remain common. Supermassive black holes, which lurk at the centers of most large galaxies, add another dimension to these cosmic collisions. When galaxies merge, their central black holes begin a gravitational dance of their own, gradually spiraling toward each other as they lose energy through interactions with surrounding stars and gas. This process can take billions of years, but eventually, the black holes themselves merge in an event so powerful it sends ripples through the very fabric of space-time, gravitational waves that spread outward at the speed of light. These waves, first directly detected in 2015 from merging stellar mass black holes, represent a new frontier in astronomy. Future space-based gravitational wave observatories may detect the mergers of supermassive black holes throughout the universe, providing a completely new way to study galaxy evolution. Each detection would mark the final chapter in a cosmic collision story that began billions of years earlier with the initial gravitational embrace of two galaxies. The ultimate fate of our universe may be determined by the ongoing battle between gravity and cosmic expansion. If the mysterious dark energy that drives the universe's accelerating expansion continues to dominate, galaxies outside our local group will eventually recede beyond our cosmic horizon, becoming permanently unreachable. The Milky Way and Andromeda will still collide and merge, along with the other members of our local group. But this might be the last major merger in our cosmic neighborhood. The resulting giant elliptical galaxy, which some astronomers have nicknamed Milkomeda, could drift through an increasingly empty universe, an island of stars in a vastly expanded cosmos. But the question remains, when galaxies collide, what happens to the stars, planets, and other structures within them? How do these cosmic train wrecks transform the galaxies involved? To understand the full drama of these encounters, we must look more closely at what happens when two galaxies begin their fateful approach. When two majestic galaxies begin their cosmic approach, they embark on a transformation so profound and beautiful that astronomers often describe it as a gravitational ballet. But unlike human dancers who complete their performance in minutes, these celestial partners move through their choreography over hundreds of millions of years. Let's walk through the stages of this cosmic dance, from first encounter to final merger, to understand how these violent yet creative events reshape the universe. The journey begins with the initial encounter, the moment when two previously separate galaxies first begin to feel each other's gravitational influence in a meaningful way. Long before their visible disks come anywhere near each other, their extended dark matter halos, invisible to our telescopes but containing most of the galaxy's mass, make first contact. These halos can extend up to 10 times farther than the visible portions of galaxies, meaning that gravitational interactions begin when the luminous parts of the galaxies are still millions of light years apart. During this early phase, subtle changes begin to reshape both galaxies. The gravitational pull of each galaxy creates tidal forces, differential gravitational effects where the near side of a galaxy feels a stronger pull than the far side. These tidal forces begin to distort the outer regions of each galaxy's disk, gently at first, like invisible hands starting to mold cosmic clay. Stars and gas at the edges of each galaxy begin to feel this disturbance first, their orbits gradually shifting in response to the gravitational intrusion. As the galaxies continue their approach, these distortions become more pronounced. The gas and stars in the outer regions of each galaxy are increasingly drawn outward, forming graceful arcs and bridges between the approaching galactic cores. These dramatic structures, known as tidal tails, can stretch for hundreds of thousands of light years, longer than the diameter of the original galaxies themselves. The tides, each galaxy pulls more strongly on the near side of its neighbor, but unlike Earth's oceans, which quickly return to normal after the tide passes, these galactic tides permanently redistribute stars and gas, painting luminous streams across the cosmos that can persist for billions of years. Computer simulations reveal that the exact shape and extent of these tidal features depend on several factors: the relative masses of the colliding galaxies, their approach angles, and their rotation directions. When a larger galaxy encounters a smaller one, the tidal forces often shred the smaller galaxy completely, stretching it into long stellar streams that wrap around the larger galaxy like cosmic ribbons. The Sagittarius Dwarf galaxy, currently being dismembered by our Milky Way, provides a front-row seat to this process. As the galaxies draw closer, their interactions intensify. The gas clouds within each galaxy, the vast reservoirs of hydrogen and helium that serve as fuel for star formation, begin to feel the effects most dramatically. Unlike stars, which are tiny points in the vastness of a galaxy and rarely collide even during galactic mergers, gas clouds are extended structures that can directly impact each other. When clouds from different galaxies meet, they don't pass through each other like ghosts. They collide, compress, and set the stage for one of the most spectacular phases of galactic mergers. This compression of gas triggers a phenomenon known as a starburst, a dramatic increase in the rate of star formation that can outshine the entire pre-collision galaxy. As gas clouds crash together at speeds of hundreds of kilometers per second, they create shock waves that compress the gas to densities thousands of times greater than normal interstellar space. Under these extreme conditions, gravity can overcome the natural pressure of the gas, causing it to collapse and fragment into thousands of dense cores that will become new stars. The starburst phase transforms the colliding galaxies into cosmic forges, creating new stars at rates hundreds of times greater than peaceful galaxies. Some of these newly formed stars are massive blue giants that burn hot and bright, with surface temperatures reaching 50,000 degrees Celsius. Though these stellar behemoths live only a few million years before dying in spectacular supernova explosions, their intense light temporarily changes the color of the merging galaxies, making them appear bluer and brighter. Astronomers can observe this starburst phase in systems like the Antennae Galaxies, located about 65 million light-years from Earth. Named for their resemblance to insect antennae due to their long tidal tails, these colliding spirals are in the midst of a star-forming frenzy, with thousands of new star clusters being born in the compressed gas where the galaxies overlap. Infrared observations reveal that much of this star formation is hidden behind thick veils of dust, with the hottest action taking place in the densest regions invisible to optical telescopes. While stars and gas perform their dramatic dance, the supermassive black holes lurking at the center of each galaxy begin their own remain embedded in dense clusters of stars. The stars act like a cosmic buffer, absorbing energy from the black holes through a process called dynamical friction. Imagine trying to walk through a dense crowd. You would bump into people, slowing your progress while transferring some of your energy to the crowd. Similarly, the black holes interact gravitationally with surrounding stars, gradually slowing down and spiraling toward each other over millions of years. When the black holes get within a few light years of each other, they form a binary system, two immense black holes orbiting a common center of mass. At this stage, they begin to fling stars away from the galactic center through gravitational slingshot effects, gradually clearing a region around themselves. This process can create a temporary depression in the center of the merging galaxy, where the stellar density is lower than in the surrounding regions. A cosmic donut with the binary black holes at its empty center. The final parsec problem, as astronomers call it, presents an intriguing puzzle in black hole mergers. As the binary black hole system continues to eject stars from its vicinity, it eventually runs out of stars to interact with, potentially stalling the merger process at a separation of about 1 parsec, roughly 3.26 light-years. However, gas clouds and gravitational waves likely provide additional mechanisms for the black holes to lose energy, allowing them to overcome this final hurdle and continue their inevitable merger. The actual merger of two supermassive black holes releases an almost unimaginable amount of energy. In the final moments, as these cosmic titans spiral into each other at near light speed, they convert a significant fraction of their mass directly into energy in the form of gravitational waves, ripples in the fabric of space-time that radiate outward at the speed of light. A typical merger might release more energy than all the stars in the observable universe combined, though this energy is carried away as gravitational waves rather than as electromagnetic radiation like light or X-rays. While this black hole drama unfolds in the galactic core, the overall structure of the merging galaxies continues to transform. The elegant spiral patterns that characterize the original disk galaxies become increasingly distorted and eventually erased. Stars that once followed orderly circular orbits around their respective galactic centers are flung into chaotic new paths. The thin disks of the original spiral galaxies puff up into thicker configurations as stars are scattered above and below the galactic plane. Gas clouds that avoided the initial compression and starburst phase eventually settle toward the center of the newly forming galaxy. This influx of gas can trigger a second, often more powerful starburst phase near the merged galactic core. It can also feed the newly united supermassive black hole, creating what astronomers call an active galactic nucleus, or AGN. As gas spirals into the black hole, it forms an intensely hot accretion disk that can outshine all the stars in the galaxy combined, potentially creating a quasar, the most luminous stable objects in the universe. The final phase of a galaxy merger is the relaxation or settling phase. which can last more than 1 billion years. During this period, the chaotic energy of the collision gradually dissipates as stars settle into stable orbits within the new galaxy. The wild distortions and tidal tails slowly fade, though they may never completely disappear. Even in fully merged galaxies, astronomers can often detect shells, streams, and other structures that bear witness to ancient collisions long after the violence has subsided. The end result of a major galaxy merger between two spiral galaxies is typically an elliptical galaxy, a rounder, smoother, and more uniformly yellow galaxy with little of the structure that characterized its spiral predecessors. These cosmic retirement communities contain mostly older stars, with relatively little gas remaining for new star formation. The wild starburst phases during the merger used up or expelled much of the original gas, leaving the resulting elliptical relatively quiescent. Not all collisions follow this exact script, however. When galaxies of very different masses collide, the larger galaxy may remain relatively intact, incorporating the stars and gas of its smaller companion without drastically changing its own structure. Our Milky Way has experienced many such minor mergers throughout its history, growing by cannibalizing smaller dwarf galaxies while maintaining its spiral structure. Current observations suggest our galaxy has absorbed at least 5 to 11 significant systems throughout its lifetime, with each one contributing stars to our galactic halo. The orientation of the collision also matters tremendously. When two disk galaxies collide edge-on, with their disks perpendicular to each other, they can sometimes preserve more of their original structure than in face-on collisions. Some peculiar galaxies with ring-like structures, such as the aptly named Cartwheel Galaxy, were likely formed when a smaller galaxy punched directly through the disk of a larger one, creating a ripple effect similar to dropping a stone into a cosmic pond. The gas content of the colliding galaxies plays a crucial role in determining the outcome. Gas-rich mergers, those involving galaxies with abundant hydrogen gas, typically produce more dramatic starbursts and can sometimes result in the formation of a new disk galaxy rather than an elliptical. By contrast, dry mergers between galaxies that have already used up or lost most of their gas typically produce elliptical galaxies with little new star formation. Throughout these stages of galactic collision, it's important to remember that the vast majority of individual stars never actually collide with each other. The distances between stars are so immense compared to their sizes that direct stellar collisions are extraordinarily rare events, even in the densest galactic cores. A typical star in the Milky Way's disk might be separated from its nearest neighbor by over 4 light-years, about 30 million times the diameter of the star itself. If stars were the size of oranges, they would be separated by thousands of kilometers on average. This vast emptiness within galaxies means that despite the violent appearance of galactic collisions in astronomical images and simulations, they unfold with surprising gentleness from the perspective of individual solar systems. When the Milky Way and Andromeda galaxies merge billions of years from now, our Sun will almost certainly not collide with another star. Instead, it will be gravitationally nudged into a new orbit within the combined galaxy, potentially carrying Earth and the other planets along for the ride, assuming our Sun hasn't already expanded into a red giant and engulfed the inner planets by that time. For planets harboring life, this relative safety is crucial. While the night sky would certainly change dramatically during a galactic collision, with new constellations forming as star systems are redistributed, the day-to-day conditions on life-supporting planets would likely remain stable. The habitability of a planet depends primarily on its distance from its host star, not on the star's position within a galaxy. So while entire solar systems might be flung into different regions of a merging galaxy, the planets would maintain their orbits around their parent stars, preserving conditions that might support life. Of course, there are exceptions to this general safety. Regions near the galactic center, where stars are packed more densely, face higher risks during mergers, and solar systems passing through active star-forming regions might encounter dangerous radiation from newly formed massive stars or their supernova explosions. But overall, galactic collisions pose less immediate danger to planetary systems than one might assume from their spectacular appearance. What makes these collisions so visually striking in astronomical images is not the movement of individual stars, but the redistribution of billions of stars together, along with the glowing gas clouds that trace these movements. When we observe systems like the antennae galaxies or the mice galaxies, we're seeing the combined light of countless stars, arranged in distorted shapes by gravitational forces acting over millions of years. The human mind can barely comprehend the scale and time span involved. Hundreds of billions of stars engaged in a dance that began before multicellular life existed on Earth and will continue long after our species has either gone extinct or evolved into something unrecognizable. As we observe galaxies in various stages of collision throughout the universe, we're witnessing not just destruction, but creation, the forging of new stellar systems, the birth of massive star clusters, and the recycling of cosmic materials into new forms. By studying these stages in different galactic interactions, astronomers can piece together the full life cycle of galaxy mergers, from the first gravitational whisper to the final settled form millions or billions of years later. Perhaps most fascinating is the realization that galactic collisions don't just reshape individual galaxies, they drive the evolution of the universe itself. Each collision and merger represents another step in the hierarchical assembly of cosmic structures, building larger and more complex systems from smaller components. Without these violent yet creative events, the universe would lack the massive galaxies and galaxy clusters that define its large-scale structure today. But what happens during the most dramatic phase of these cosmic collisions, when compression waves sweep through vast clouds of gas, triggering the birth of new stars at an astonishing rate? This starburst phenomenon represents one of the most creative consequences of galactic violence, and it's to this stellar baby boom that we now turn our attention. Amid the chaos and disruption of colliding galaxies lies a profound irony. These violent encounters rank among the most creative events in the universe. As massive star systems are torn apart by gravitational forces, they simultaneously give rise to millions of new suns, potentially surrounded by planets that might one day harbor life. This cosmic creation amidst destruction reveals the cyclical nature of our universe, where endings become beginnings in an endless tapestry of stellar evolution. To understand how galactic collisions trigger star formation, we must first examine the raw material from which stars are born, the vast, cold clouds of molecular hydrogen that drift through the seemingly empty space between existing stars. These stellar nurseries, often called molecular clouds, can span hundreds of light years and contain enough material to create thousands or even millions of new stars. In undisturbed galaxies, these clouds exist in a delicate gravitational balance, neither collapsing under their own weight nor dispersing into the surrounding space. What makes galactic collisions so effective at triggering star formation is their ability to disrupt this balance. As two galaxies pass through each other, their gas clouds don't simply slide past like ghosts. Instead, they collide and compress, creating shockwaves that ripple through the molecular clouds. These shockwaves act like cosmic bulldozers, pushing gas molecules closer together and raising both density and pressure. When the density in a region becomes high enough, gravity takes over, pulling the gas into an ever tighter sphere that eventually becomes hot and dense enough to ignite nuclear fusion, the birth of a new star. Observations of colliding systems like the antennae galaxies reveal this process in spectacular detail. Hubble Space Telescope images show thousands of bright blue star clusters forming along the regions where the two galaxies overlap. Each of these clusters contains thousands of newly formed stars, many of them massive, hot, and luminous. These stellar newborns shine with a distinctive blue light because of their high surface temperatures, often exceeding 25,000 degrees Celsius. What's particularly fascinating about collision-induced star formation is its efficiency. Under normal conditions in a spiral galaxy like our Milky Way, only about 1% of the available gas is converted into stars each year. But in colliding systems, this rate can increase by factors of 10, 100, or even 1,000. galaxies undergoing major mergers can transform hundreds of millions of solar masses of gas into new stars in a relatively brief cosmic moment, creating a brilliant but temporary surge in the galaxy's overall luminosity. This phenomenon, known as a starburst, often outshines the rest of the galactic merger. Many of the most luminous galaxies in our universe are actually systems in the throes of collision-induced starbursts. These aptly named luminous infrared galaxies, or LRGs, radiate energy equivalent to over 1 trillion suns, with most of that energy coming from newly formed stars and the heated dust surrounding them. The most extreme examples, ultra-luminous infrared galaxies, or ULIRGs, can shine with the light of over 10 trillion suns, bright enough to be visible across billions of light-years of space. Why do these starbursts appear so bright in infrared light, rather than visible light? The answer lies in the dusty environments in which they occur. The same gas-rich regions that fuel rapid star formation also contain tiny particles of cosmic dust, microscopic grains of carbon, silicon, and other elements produced in previous generations of stars. This dust absorbs much of the visible light from new stars and re-emits it as infrared radiation, creating a cosmic veil that only infrared telescopes can penetrate. The James Webb Space Telescope, with its unprecedented infrared vision, has revolutionized our understanding of these dusty starbursts. Peering through the cosmic fog, it reveals details of star formation in colliding galaxies that were previously invisible to instruments like Hubble, which primarily observe invisible light. These observations confirm that the most intense star formation often takes place in the densest, most dust-enshrouded regions, where the galaxy's gas supplies directly interact. The stars born during these collision-induced bursts aren't distributed randomly throughout the merging galaxies. Instead, they form in distinct patterns that trace the dynamics of the interaction. In the early stages of a collision, new stars often appear in spiral arms that have been enhanced and distorted by gravitational forces. As the merger progresses, star formation concentrates along tidal bridges connecting the galaxies and in the central regions where gas accumulates. In late-stage mergers, the most intense star formation typically occurs near the center of the combined system, where gas from both galaxies has pooled together. Not all newly formed stars are created equal. The compression of gas during galactic collisions tends to favor the formation of massive stars, cosmic giants with 10, 20, or even 100 times the mass of our Sun. These stellar behemoths burn bright and hot, fusing hydrogen at tremendous rates that make them thousands of times more luminous than stars like our Sun. But this brilliant existence comes at a cost. These massive stars live fast and die young, with lifespans measured in millions rather than billions of years. The predominance of massive star formation during galactic collisions creates spectacular but short-lived starbursts. After a few million years, the largest stars begin to die in supernova explosions, their brief lives ending in blasts that outshine their entire home galaxies for a few weeks. These explosions scatter newly forged heavy elements into the surrounding gas, enriching it with carbon, oxygen, silicon, iron, and other elements essential for planet formation and potentially for life. This enrichment process highlights one of the most profound aspects of collision-induced star formation, its role in creating the chemical diversity necessary for complex cosmic structures. The early universe contained almost exclusively hydrogen and helium, elements too simple to form the complex molecules needed for planets and life. It was only through generations of stars creating heavier elements and then distributing them through supernovae that the universe gained the chemical complexity we see today. Galactic collisions accelerate this enrichment by triggering waves of star formation and subsequent supernovae, particularly of massive stars that produce the largest quantities of heavy elements. The most dramatic mergers can compress billions of years of steady chemical enrichment into explosive episodes lasting just millions of years. This rapid processing creates pockets of gas with unusually high concentrations of heavy elements, cosmic forges where future generations of stars will have abundant materials to form rocky planets. Of particular interest to astrobiologists, scientists who study the potential for life beyond Earth, are elements like carbon, oxygen, nitrogen, phosphorus, and sulfur. These elements form the backbone of organic molecules and are essential for life as we know it. All of them are created inside stars and distributed through space via stellar winds and supernova explosions. By triggering waves of stellar birth and death, galactic collisions help ensure that these vital elements become available for planet formation and potential biological processes. The formation of star clusters represents another key feature of collision-induced star formation. Rather than creating isolated stars, galactic mergers tend to produce dense clusters containing thousands or even millions of stars in relatively compact regions. Some of these clusters, particularly those with enough mass to remain gravitationally bound despite supernova explosions and other disruptive forces, may survive as globular clusters, ancient spherical collections of stars that orbit the merged galaxy for billions of years. Observations of nearby galaxy mergers suggest that up to 40% of all stars formed during major collisions arise within these dense clusters. The antennae galaxies alone contain over 1,000 superstar clusters, extraordinarily dense stellar cities, each containing up to millions of stars in regions just a few dozen light-years across. These clusters represent one of the most dramatic signatures of collision-induced star formation, creating brilliant knots of light that stand out even against the bright background of merging galaxies. For planets and potential life, these star-forming environments present both opportunities and challenges. On one hand, the enrichment of gas with heavy elements creates ideal conditions for forming rocky planets with diverse mineral compositions. On the other hand, the presence of numerous massive stars means high levels of ultraviolet radiation and frequent supernovae, conditions potentially hostile to fragile biological processes. However, not all star formation occurs in these extreme environments. As merging galaxies continue their dance, gas compression happens in many regions, not just the most intense starburst zones. More moderate environments, similar to the spiral arms of our own Milky Way, can form stars of lower mass, including those similar to our Sun. These stars may owe its existence to gas enriched by multiple generations of stars, some formed during ancient galactic encounters. The future merger between our Milky Way and the Andromeda Galaxy, expected to begin in about 4 billion years, will write a new chapter in this ongoing story of cosmic creation. Computer simulations predict substantial new star formation as gas clouds from the two galaxies collide and compress. By that distant future, our Sun will be nearing the end of its life as a main sequence star, beginning to expand into a red giant. Any new stars and planets formed during this merger will arise in a very different solar neighborhood than the one we know today. As we observe colliding galaxies across the universe, we're witnessing not just the transformation of these massive stellar cities, but also the creation of new suns and potentially life-supporting worlds. Each bright knot of star formation visible in these cosmic train wrecks represents thousands of new stellar systems, each with its own potential for planets and possibly life. The destruction wrought by these titanic collisions simultaneously sows the seeds for a new generation of cosmic creativity. In the grand scheme of cosmic evolution, galactic collisions serve as natural accelerators, compressing billions of years of gradual star formation into relatively brief episodes of intense stellar birth. These events don't just reshape the visible structure of galaxies, they fundamentally alter their composition, enriching them with heavy elements and redistributing their stars into new configurations. The result is a universe constantly renewed through cycles of destruction and creation, where even the most violent events contribute to the increasing complexity and diversity of cosmic structures. But not all the action in galactic collisions takes place in the visible realm of stars and gas. At the centers of most large galaxies lurk supermassive black holes. cosmic monsters with masses millions or billions of times that of our Sun. When galaxies collide, these behemoths begin their own dance of destruction, with consequences that can reshape entire galactic systems and send ripples through the very fabric of space-time itself. At the heart of nearly every large galaxy in our universe lurks an object so extreme it defies ordinary comprehension: a supermassive black hole. These cosmic leviathans, with masses ranging from millions to billions of times that of our Sun, represent the ultimate expression of gravity's power to warp the very fabric of space and time. When galaxies collide, these central behemoths engage in a gravitational dance of their own, with consequences that can reshape entire galactic systems and release energy on truly astronomical scales. The supermassive black hole residing at the center of our own Milky Way, known as Sagittarius A star, has a mass of about 4 million suns. Yet despite this enormous mass, it's relatively modest compared to those found in larger galaxies. The central black hole in the giant elliptical galaxy, Messier 87, made famous by the first direct image captured by the Event Horizon Telescope, weighs in at about 6.5 billion solar masses, and some monster black holes in distant quasars may reach 10 billion solar masses or more, cosmic dragons large enough to swallow our entire solar system with room to spare. How these supermassive black holes formed remains one of the greatest mysteries in modern astronomy. Some theories suggest they grew from stellar mass black holes, those formed when massive stars collapse, which then merged and accumulated matter over billions of years. Other models propose that they formed directly from the collapse of enormous gas clouds in the early universe, bypassing the stellar stage entirely. Regardless of their origin, these massive objects now sit at the gravitational throne of almost every large galaxy, influencing stellar orbits and gas dynamics throughout their domain. When two galaxies begin their long journey toward merger, their central black holes initially remain separated by vast distances, typically tens of thousands of light years during the early stages of collision. At this point, each black hole continues to influence only the stars and gas in its immediate vicinity. But as the merger progresses and the galactic cores approach each other, the black holes begin to feel each other's gravitational pull, setting the stage for one of the most extreme events in the universe: the merger of two supermassive black holes. This process unfolds in several distinct phases, each with its own timeline and physical characteristics. During the early stages of the galactic merger, the black holes approach each other relatively slowly as they remain embedded within their respective galactic nuclei. Each black hole travels with its entourage of stars and gas, following the overall motion of its host galaxy's core. This phase can last hundreds of millions of years as the galactic cores gradually spiral toward each other through dynamical friction, the gravitational drag created as they move through the stellar field of the combined galaxy. When the galactic cores finally merge, the black holes find themselves sharing the same dense stellar environment, typically separated by a few hundred light years. At this point, they form a bound system, orbiting their common center of mass. But they're still far too distant to directly influence each other with their event horizons or accretion disks. Two black holes begin to form a true binary system, essentially becoming a gravitationally bound pair orbiting a common center. At this stage, they begin to interact more strongly with their shared environment, flinging stars away from the galactic center through gravitational slingshot effects. Stars that pass close to the binary can receive tremendous gravitational kicks, boosting them to velocities that may even exceed the galaxy's escape velocity, ejecting them into intergalactic space as hypervelocity stars. This ejection of stars creates a fascinating phenomenon, a gradually expanding loss cone of stellar orbits that have been cleared out by the binary black hole system. Astronomers can potentially detect this signature in the centers of galaxies that have recently undergone mergers, providing indirect evidence for binary, supermassive black holes, even when they're too close together to be visually resolved by our telescopes. As the black holes continue to expel stars from their vicinity, they encounter what astronomers call the final parsec problem. A parsec, equivalent to about 3.26 light years, represents a critical threshold in black hole mergers. Once the binary system has ejected most of the stars capable of interacting with it, the black holes risk becoming stranded at this separation, lacking a mechanism to dissipate further energy and complete their merger. However, nature appears to have solutions to this cosmic impasse. Gas clouds that accumulate in the galactic center can create drag on the orbiting black holes, helping them overcome the final parsec barrier. Additionally, if a third black hole enters the system, perhaps from a subsequent galaxy merger, it can destabilize the binary through complex three-body interactions, potentially driving the original pair closer together. The most important mechanism for completing the merger, however, comes from Einstein's general theory of relativity. As the black holes orbit each other at close range, they generate ripples in the fabric of space-time called gravitational waves. These waves carry away energy and angular momentum from the system, causing the black holes to spiral ever closer together in an accelerating cosmic waltz. In the final stages, as the black holes approach within a few 100 million kilometers of each other, roughly the distance from Earth to the Sun, this process dramatically accelerates. The last moments of a supermassive black hole merger represent one of the most energetic events in the universe. As the black holes make their final plunge, they reach speeds approaching that of light, releasing enormous energy in the form of gravitational waves. In the final second before merger, the power emitted in these space-time ripples can briefly exceed the combined electromagnetic radiation of all the stars in the observable universe. Yet this tremendous outburst remains invisible to conventional telescopes, which detect only electromagnetic radiation like light, radio waves, or X-rays. Gravitational waves from merging stellar mass black holes were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, opening a new window on the universe. But supermassive black hole mergers produce gravitational waves at much lower frequencies, beyond the range of ground-based detectors like LIGO. Future space-based observatories, such as the planned Laser Interferometer Space Antenna, LISA, will be designed specifically to catch these cosmic bass notes, the gravitational rumbles of merging giants that have been traversing the cosmos for billions of years. Once merged, the resulting single supermassive black hole must settle down to a stable state. This process, called ringdown, involves the newly formed black hole oscillating like a struck bell, emitting more gravitational waves as it settles into its final form. The merged black hole typically receives a substantial kick from asymmetries in the gravitational wave emission, potentially sending it recoiling through the galaxy at hundreds or even thousands of kilometers per second. In extreme cases, this kick might even eject the black hole from its host galaxy entirely, creating a rare rogue supermassive black hole wandering through intergalactic space. More commonly, the merged black hole eventually settles at the center of the newly formed galaxy, where it can strongly influence the surrounding environment. The merger process often channels large amounts of gas toward the galactic center, providing fuel for the black hole's accretion disk, the swirling maelstrom of superheated matter spiraling toward the event horizon. As this gas falls inward, it heats to millions of degrees, emitting enormous energy across the electromagnetic spectrum, from radio waves to gamma rays. This feeding frenzy can transform the combined galaxy into what astronomers call an active galactic nucleus, or AGN. In these systems, the central black hole's accretion disk can outshine all the galaxy's stars combined, creating cosmic beacons visible across billions of light-years of space. The most extreme examples, called quasars, represent the most luminous, stable objects in the universe, with some radiating energy equivalent to trillions of suns from regions no larger than our solar system. Observations suggest that galaxy mergers play a crucial role in triggering this AGN activity. The gravitational disruption caused by the collision can funnel gas from the extended regions of the merging galaxies toward their centers, providing fuel for the central black holes. Statistical studies show that AGNs are more common in disturbed interacting galaxies than in isolated ones, particularly during the late stages of mergers when the galaxy's cores combine. These active black holes don't just shine brightly, they can profoundly influence their host galaxies through a process astronomers call feedback. As the black hole consumes matter, it can generate powerful winds and jets that sweep through the surrounding galaxy like cosmic hurricanes. These outflows, moving at speeds approaching that of light, can heat or even expel cool gas clouds that would otherwise form new stars. In this way, the awakened black hole can regulate or even terminate star formation throughout the galaxy, effectively determining its future evolutionary path. This feedback process helps explain a puzzling correlation astronomers have observed. The mass of a galaxy's central black hole appears tightly linked to properties of the galaxy's central bulge of stars, such as its velocity dispersion or total mass. This relationship, often called the M-sigma relation, suggests that black holes and their host galaxies evolve together in a kind of cosmic symbiosis, each influencing the other's growth and development. Galaxy mergers represent critical moments in this co-evolution, when both the black hole and its galactic home undergo rapid, dramatic changes. Supermassive black hole mergers may also help explain another cosmic mystery, the origin of the most energetic particles known in the universe. Ultra-high energy cosmic rays, with energies millions of times greater than those achieved in our most powerful particle accelerators, occasionally strike Earth's atmosphere from deep space. Some theories suggest that the enormous electromagnetic fields generated during supermassive black hole mergers could accelerate charged particles to these extreme energies, making galactic collisions the ultimate particle accelerators. Perhaps most intriguing is the possibility that merged binary black holes might retain long-term memory of their violent origins. Theoretical models suggest that the final black hole's spin axis should align with the orbital axis of the original binary system, rather than with either of the initial black holes. By measuring the spins of supermassive black holes in post-merger galaxies, astronomers might one day reconstruct their merger histories, reading the violent past of these cosmic leviathans from their current properties. The fate of the merged supermassive black hole is tied to the fate of its host galaxy. In the case of major mergers that produce elliptical galaxies, the black hole typically ends up at the center of a relatively gas-poor environment. Without a steady supply of new gas, its accretion disk gradually fades, and the once brilliant quasar subsides into quiescence. This pattern helps explain why the most powerful quasars were more common billions of years ago, when the universe was younger and galaxy mergers more frequent. Our own Milky Way's central black hole, Sagittarius, a larger black hole with a mass of about 100 million suns. Computer simulations of this future merger suggest that the combined Milky Way Andromeda system, sometimes called Milkomeda, will likely experience enhanced star formation as gas clouds collide, potentially accompanied by increased activity from one or both central black holes as they consume disturbed gas. Eventually, the black holes will find each other and merge, releasing tremendous energy in gravitational waves and possibly generating brilliant jets visible from millions of light years away. Even dormant supermassive black holes can suddenly awaken when presented with a cosmic meal. Astronomers occasionally observe what are called tidal disruption events, brilliant flares of light that occur when a star passes too close to a supermassive black hole and is torn apart by tidal forces. These unfortunate stars are stretched into long streamers of gas, some of which escapes into space while the rest plunges onto the black hole, creating a temporary accretion disk and a brilliant burst of radiation across multiple wavelengths from radio to X-rays. Such events offer a preview of what happens on a much larger scale during galactic mergers, when not just individual stars, but entire clusters of stars and massive gas clouds are driven toward hungry, central black holes. The resulting light shows can temporarily transform quiet galactic nuclei into blazing quasars, visible across cosmic distances as beacons marking sites of galactic violence and transformation. As we observe colliding galaxies throughout the universe, we're witnessing not just the merger of vast collections of stars, but also the impending marriages of these central cosmic monsters. their gravitational dances, and eventual unions release energy on scales difficult to comprehend while simultaneously helping to shape the evolution of their host galaxies. Far from being mere passive spectators to galactic collisions, supermassive black holes play starring roles in these cosmic dramas, their influence extending far beyond their event horizons to affect billions of stars across thousands of light years. To see the aftermath of these spectacular collisions in all their glory, we need only look to some of the most striking objects in our night sky, galaxies that bear the unmistakable signatures of recent cosmic violence. These galactic fossils, frozen in various stages of collision and merger, provide a stunning gallery of cosmic crash scenes that astronomers can study to reconstruct the violent history of our universe. Across the vast expanse of our observable universe, astronomers have catalogued countless galaxies caught in various stages of collision and merger. These cosmic crash scenes serve as frozen moments in a drama that unfolds over hundreds of millions of years, allowing us to piece together the full life cycle of galactic interactions. Like cosmic forensic scientists, astronomers study these spectacular systems to understand both the violent history of our universe and the ultimate fate that awaits many galaxies, including our own Milky Way. Perhaps the most iconic and well-studied example of galaxies in mid-collision is the system known as the Antennae Galaxies, officially catalogued as NGC 4038 and NGC 4039. Located approximately 60 million light-years from Earth in the constellation Corvus, this pair of spiral galaxies began their gravitational dance about 600 million years ago. Their name derives from the two enormous tidal tails of stars, gas, and dust that extend from the main bodies of the galaxies, resembling the antenna of an insect when viewed from Earth. The Hubble Space Telescope has captured breathtaking images of this cosmic train wreck, revealing not just destruction, but an extraordinary burst of creation. The regions where the two galaxies overlap glow with the light of newly formed star clusters, appearing as bright blue knots against the yellow glow of older stars. Infrared observations penetrate the thick clouds of dust that obscure much of this starburst activity in visible light, revealing an even more intense region of star formation hidden from optical telescopes. What makes the Antennae Galaxies particularly valuable to astronomers is that they represent a middle stage in the merger process. The galaxies' cores remain distinct, separated by about 30,000 light-years, yet they're clearly bound together in a gravitational embrace that will eventually unite them. Computer simulations suggest that the galaxies have already made their closest approach and are now moving apart again, but they remain gravitationally bound and will eventually fall back together, forming a single elliptical galaxy. Another spectacular example of cosmic collision is found in the system poetically named the Mice, or more formally, NGC 4676. Located about 300 million light-years away in the constellation Coma Berenices, this pair of spiral galaxies earned their nickname because their long tidal tails resemble mouse tails. These enormous streamers of stars were pulled out from each galaxy during their close encounter, about 160 million years ago. The Mice represent an earlier stage in the merger process than the antennae. The two galaxies have made their first close pass, but haven't yet begun to merge in earnest. Their distinct spiral structures remain largely intact, though clearly distorted by gravitational forces. Eventually, they too will fall back together for increasingly close encounters, ultimately merging into a single galaxy over the next few 100 million years. Perhaps the most unusual collision remnant in our cosmic neighborhood is the Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor. This striking system represents the aftermath of what astronomers call a bullseye collision, where a smaller galaxy punched directly through the disk of a larger spiral galaxy. The result looks uncannily like a cosmic wagon wheel, with a bright central hub surrounded by a ring-like structure that continues to expand outward into space. The collision that created the cartwheel occurred about 200 million years ago, sending a compression wave radiating outward through the larger galaxy's disk, much like ripples spreading across a pond after a stone is dropped into it. This expanding wave triggered intense star formation as it moved outward, leaving behind a ring of bright, newly formed stars with a diameter of about 150,000 light-years, larger than our entire Milky Way galaxy. The cartwheel offers a perfect example of how galactic collisions don't always lead to conventional mergers. In this case, the smaller intruder galaxy passed completely through its larger companion and is now visible as a separate structure some distance away. The larger galaxy was dramatically reshaped by this cosmic puncture wound, transforming from a typical spiral into the distinctive wheel-like structure we see today. Closer to home, we find the captivating system Messier 51, better known as the Whirlpool Galaxy. Located about 23 million light-years away in the constellation Canes Venatici, this face-on spiral galaxy is interacting with a smaller companion, NGC 5195. Their gravitational dance has enhanced and distorted the Whirlpool's spiral structure, creating one of the most photogenic galaxies in our night sky. Unlike more advanced mergers like the antennae, the Whirlpool interaction is in a relatively early stage. The smaller companion galaxy has made a close pass, tugging on the Whirlpool's outer regions and drawing out a stream of stars between the two systems. This gravitational disturbance has stimulated waves of star formation along the Whirlpool's enhanced spiral arms, which glow with the light of hot, massive, newly formed stars. But the most personally relevant galactic collision for Earth's inhabitants is the impending merger between our Milky Way and the neighboring Andromeda Galaxy, or Messier 31. Currently separated by about 2.5 million light-years, these spiral giants are moving toward each other at roughly 110 kilometers per second. Precise measurements by the Hubble Space Telescope confirm that the two galaxies will experience their first close pass in about 4.5 billion years, with complete merger following a few billion years later. This future collision, nicknamed Milkomeda by astronomers, provides a fascinating case study because we know both participants intimately. Our Milky Way is a barred spiral galaxy containing at least 200 billion stars, with a supermassive black hole of about 4 million solar masses at its center. Andromeda is somewhat larger, hosting perhaps as many as 1 trillion stars and a central black hole roughly 25 times more massive than ours. When these galaxies collide, the night sky for any observers still present on Earth will undergo a dramatic transformation. Computer simulations suggest that during the first close approach, Andromeda will appear as an enormous spiral structure dominating the night sky, spanning many times the apparent width of the full moon. As the galaxies pass through each other and then fall back together over billions of years, stars from both systems will be flung into new orbits, completely reorganizing our cosmic neighborhood. How this danger might come from gravitational disturbances to the Oort Cloud, the sphere of icy bodies surrounding our solar system, which could potentially send comets hurtling toward the inner planets. By the time the Milky Way and Andromeda complete their merger, our Sun will have evolved off the main sequence into a red giant and then a white dwarf, potentially engulfing the inner planets in the process. Any observers still present would witness the final product, likely a giant elliptical galaxy containing the combined stars of both original systems, with little of the spiral structure that once characterized these majestic galaxies. The history of cosmic collisions is written not just in spectacular ongoing mergers, but in the subtle structures of seemingly isolated galaxies. Stellar streams, shells, and warped disks serve as fossil evidence of past gravitational encounters, allowing astronomers to reconstruct the violent histories of galaxies that appear relatively peaceful today. Even our own Milky Way bears such scars, with structures like the Sagittarius Stream revealing the ongoing disruption of smaller galaxies that ventured too close to our galactic home. As we continue to observe these cosmic crash scenes with increasingly powerful telescopes, each new image and measurement helps refine our understanding of how galaxies evolve through collisions and mergers. From the dramatic beauty of the antennae to the impending embrace of the Milky Way and Andromeda, these cosmic encounters remind us that the universe is not static but dynamic, constantly changing and evolving through processes both violent and creative, operating on timescales that dwarf human experience but fall within the reach of our scientific understanding. Through the study of these galactic fossils and ongoing collisions, astronomers are gradually piecing together a comprehensive picture of galactic evolution, one that explains not just why galaxies collide, but how these collisions have shaped the universe we see today. To fully appreciate this grand cosmic narrative, we must step back from individual collision events and consider their collective role in the broader story of galactic evolution, a tale that spans almost the entire history of our universe. When the cosmic dust settles after a galactic collision, the resulting systems bear little resemblance to their progenitors. These transformed galaxies represent not just the aftermath of destruction, but the beginning of a new chapter in cosmic evolution. By studying galaxies in various post-collision states, astronomers can piece together how these violent encounters have shaped the universe we see today, and how they will continue to mold its future. The most common outcome of major galaxy mergers, those between galaxies of similar mass, is the formation of elliptical galaxies. Unlike the flat, disc-shaped spirals with their elegant arm patterns, ellipticals appear as three-dimensional, football-shaped collections of stars with smooth, featureless structures. These cosmic retirement communities typically contain older, redder stars with relatively little ongoing star formation and minimal reserves of cold gas and dust, the raw materials needed to create new stars. This transformation from structured spirals to smooth ellipticals represents one of the most dramatic metamorphoses in the universe. Computer simulations reveal how this process unfolds. As spiral galaxies merge, their orderly rotating disks are disrupted by gravitational forces, flinging stars onto random, chaotic orbits. Stars that once traveled in neat circular paths around their galactic centers find themselves on elongated, elliptical trajectories that take them far above and below the original galactic plane. The gas that once formed the raw material for star formation in the original spirals meets several possible fates during a major merger. Some is compressed to high densities, triggering bursts of star formation that rapidly convert gas into stars. Some falls toward the center, potentially feeding the supermassive black hole and triggering an active galactic nucleus. And some may be heated and expelled from the galaxy entirely by powerful outflows driven by supernovae or the central black hole. The end result is a gas-poor system with little capacity for creating new stars. This process helps explain one of the great mysteries in galaxy evolution: why the universe contains two main types of galaxies with seemingly distinct properties. Astronomers have long recognized a bimodal distribution in the galaxy population: blue, star-forming spirals on one hand, and red, quiescent ellipticals on the other. Galaxy mergers provide a mechanism for transforming one type into the other, moving galaxies from the blue cloud to the red sequence on astronomical color magnitude diagrams. The largest elliptical galaxies, often found at the centers of galaxy clusters, likely formed through multiple successive mergers throughout cosmic history. These galactic giants, sometimes called CD galaxies by astronomers, can span millions of light years and contain trillions of stars. Cosmic behemoths that may be hundreds of times more massive than our Milky Way. Their formation histories are written in their extended structures, which often feature faint outer envelopes of stars stretching far beyond their main bodies. But not all galaxy mergers result in ellipticals. When gas-rich spirals merge under specific conditions, particularly when they have similar masses and their rotation axes are aligned, the resulting galaxy may retain, or even rebuild, a disk structure. These remnant disks demonstrate the resilience of cosmic structures and the complexity of merger dynamics. The presence of abundant gas seems to be the key factor, as it can absorb and redistribute angular momentum, helping to maintain or restore rotational support against gravitational forces that would otherwise create a more spheroidal system. Observations suggest that many massive disk galaxies in the present-day universe, including potentially our own Milky Way, may have experienced major mergers in their distant past without transforming into ellipticals. These systems somehow maintained or regained their disk structures despite the gravitational violence they experienced. Understanding how this occurs remains an active area of research. with important implications for how we interpret the evolutionary history of galaxies we observe today. One of the most striking features of post-merger galaxies is the presence of shells, streams, and other substructures that can persist for billions of years after the collision itself is complete. These features form as stars from the disrupted galaxies continue to oscillate through the merged system, creating visible ripples and arcs that slowly fade with time. By identifying and mapping these subtle structures, astronomers can reconstruct the merger histories of seemingly isolated galaxies, reading their violent paths from these fading cosmic scars. Our own Milky Way bears such signatures of past mergers. Detailed mapping of stars in our galaxy's halo reveals a complex network of streams and overdensities. The ghosts of dwarf galaxies torn apart by our galaxy's gravitational field. The most prominent is the Sagittarius stream, the remains of a dwarf galaxy currently being shredded as it orbits and gradually merges with the Milky Way. These structures tell us that our galaxy, far from evolving in isolation, has grown by consuming smaller neighbors throughout its history. This process of galactic cannibalism, where larger galaxies grow by absorbing smaller ones, represents a key mechanism of hierarchical galaxy assembly, the bottom-up process through which cosmic structures form. In this picture, small galaxies form first in the early universe, then gradually merge to create increasingly massive systems. The largest galaxies we see today, with their complex merger histories, represent the culmination of this process, having incorporated stars that originally formed in many different progenitor galaxies. The chemical composition of stars provides another window into this assembly history. Stars retain the chemical signatures of the gas from which they formed, carrying this information like cosmic DNA through subsequent mergers and interactions. By studying the abundances of different elements in stars throughout a galaxy, astronomers can identify distinct populations with different origins. Some stars in our Milky Way's halo show chemical patterns that differ from those in the disk, suggesting they formed in separate systems that were later accreted. Central to this evolutionary process is the role of dark matter, the invisible substance that makes up roughly 85% of the matter in the universe. Dark matter halos surrounding galaxies extend far beyond their visible components and interact first during galactic approaches. These halos don't just bring galaxies together, they also provide the gravitational scaffolding that determines the final shape of merged systems. The distribution of dark matter influences everything from rotation curves to star formation patterns in post-merger galaxies. The violence of galaxy mergers can also have profound effects on the gas content and star formation potential of the resulting systems. Major mergers often trigger intense but short-lived bursts of star formation that can convert a significant fraction of the available gas into stars within just a few 100 million years. This rapid depletion, combined with gas heating and expulsion by energetic processes, can effectively terminate a galaxy's capacity for creating new stars, a process astronomers call quenching. This quenching mechanism helps explain the evolution of the most massive galaxies in our universe. Observations show that many massive galaxies formed most of their stars early in cosmic history and have remained relatively dormant for billions of years since. Major mergers provide a way to both trigger intense early star formation and then shut it down by depleting, heating, or expelling the remaining gas. The largest elliptical galaxies, with their ancient stellar populations and minimal ongoing star formation, represent the end products of this process. The supermassive black holes at the centers of galaxies play a crucial role in this quenching process. During galaxy mergers, large amounts of gas are funneled toward the center, potentially feeding the black hole and triggering an active galactic nucleus, AGN. The enormous energy released by this activity can heat or expel gas throughout the galaxy, effectively sterilizing it against future star formation. This AGN feedback process creates a self-regulating system that links black hole growth to the evolution of the host galaxy. This connection helps explain one of the most remarkable discoveries in extragalactic astronomy, the tight correlation between the mass of a galaxy's central black hole and properties of its stellar bulge. Somehow, despite the enormous difference in scale between a supermassive black hole, comparable in size to our solar system, and its host galaxy, spanning tens of thousands of light-years, these components seem to know about each other and grow in lockstep. Galaxy mergers and the feedback processes they trigger provide a mechanism for establishing and maintaining this correlation. The consequences of galaxy evolution extend far beyond the individual systems involved. The metals, elements heavier than hydrogen and helium, produced in stars and distributed through space via supernovae and galactic outflows, enrich the intergalactic medium, changing the composition of gas available for forming future generations of stars and galaxies. By triggering intense star formation and powerful outflows, galaxy mergers accelerate this enrichment process, gradually increasing the universe's chemical complexity over cosmic time. This enrichment has profound implications for the formation of planets and potentially for life itself. Elements like carbon, oxygen, silicon, and iron, essential components of terrestrial planets and biological systems, were largely absent in the early universe. They had to be created in stellar furnaces and distributed through space before planets like Earth could form. By driving waves of star formation and element production, galaxy mergers have helped create the conditions necessary for our existence. As we look toward the future of cosmic evolution, the role of galaxy mergers appears set to diminish. The accelerating expansion of the universe, driven by the mysterious force known as dark energy, is gradually increasing the separation between galaxy clusters, making future intercluster mergers increasingly unlikely. Over incredibly long timescales, trillions of years, galaxies within bound groups and clusters will likely merge into single massive systems, while the spaces between these isolated island universes grow ever vaster. Our own local group will follow this pattern. After the Milky Way and Andromeda complete their merger in the distant future, the resulting Milkomeda galaxy will likely go on to absorb the other, smaller members of our local collection of galaxies. Eventually, this process will create a single massive galaxy containing virtually all the stars currently spread throughout the local group. This isolated island will drift through an increasingly empty cosmos as other galaxy clusters accelerate beyond our cosmic horizon, never to be seen again. This future scenario represents the ultimate aftermath of galactic destruction, a universe of isolated island galaxies, each the product of numerous mergers, floating in an ever-expanding void. The creative violence of galactic collisions, which has shaped cosmic evolution since the first galaxies formed, will gradually come to an end, replaced by the eternal isolation of these final merged systems. The story of galactic evolution through mergers and collisions speaks to broader themes in our understanding of the cosmos. The universe displays a remarkable duality between competition and cooperation, destruction and creation. The same gravitational forces that tear apart the ordered structures of colliding galaxies also trigger the birth of new stars and the redistribution of life-giving elements. What appears as violence on one scale enables creation on another. This perspective encourages us to see galaxy mergers not as cosmic catastrophes, but as essential components in the grand cycle of cosmic evolution. The elliptical galaxies that result from major mergers aren't failed or destroyed systems, but rather mature products of an ongoing universal process. Cosmic retirement communities that bear witness to rich and complex histories of interaction and transformation. As we continue to observe galaxies at different stages of interaction and merger across different cosmic epochs, we refine our understanding of how these processes have shaped the universe we inhabit. Each collision and merger represents another thread in the cosmic tapestry, contributing to the rich diversity of galaxies we see today and setting the stage for the universe of tomorrow. But even though galaxies collide and stars are flung into new orbits, what happens to the planets and solar systems caught in this cosmic restructuring? Could life survive the chaos of these galactic transformations? To answer these questions, we must examine the collision process at a more personal scale, the fate of habitable worlds during the greatest restructuring events in cosmic history. As we contemplate the cosmic drama of colliding galaxies, A question naturally arises: what would happen to life-bearing worlds caught in these titanic events? Would planets like Earth survive the chaos of galaxies in collision, or would nascent biospheres be extinguished in the cosmic crossfire? The answer reveals a surprising truth about the scale and nature of galactic interactions and offers insights into our own planet's future when the Milky Way and Andromeda begin their gravitational dance billions of years from now. Despite the catastrophic appearance of galactic collisions, with their distorted shapes and drawn-out tidal tails, the fate of individual solar systems is far less dramatic than we might imagine. The key to understanding this apparent paradox lies in the vast emptiness of space. Galaxies may contain hundreds of billions of stars, but the distances between these stars are truly enormous. In our solar neighborhood, the nearest star system, Alpha Centauri, lies over 4 light-years away, about 40 trillion kilometers. If our sun were represented by a grain of sand, the nearest star would be another grain of sand over 200 kilometers away. These vast interstellar distances mean that even during the chaotic merger of two massive galaxies, direct collisions between stars remain extraordinarily rare events. Astronomers estimate that when the Milky Way and Andromeda galaxies collide in roughly 4 billion years, the chance of our Sun physically encountering another star is less than 1 in a million. The same protective buffer of empty space would apply to virtually all planetary systems caught in galactic mergers throughout the universe. What would happen instead is a gradual, almost imperceptible change in each star's galactic orbit. As the gravitational forces of the colliding galaxies redistribute stars into new paths, solar systems would find themselves traveling through different regions of the merged galaxy. A star that once orbited in a spiral arm might be thrown into the galactic halo slowly over hundreds of millions of years, that it would be imperceptible to any civilization existing on the planets of these systems. From the perspective of a hypothetical observer on a planet like Earth, the most noticeable effect of a galactic collision would be a gradually changing night sky. As neighboring stars shift to new orbits, familiar constellations would slowly distort and transform over millions of years. New bright stars might appear as once distant suns are brought nearer by gravitational reshuffling. And during close approaches between the merging galaxies, the night sky might be filled with the spectacular vision of another galaxy spanning a large portion of the visible heavens, a cosmic spectacle far grander than any astronomical sight in Earth's current skies. While the stars themselves would remain safely separated, planetary systems could face more subtle hazards during galactic mergers. One concern involves the Oort Cloud, the sphere of icy bodies that surrounds our solar system at distances of up to 1 or 2 light-years from the Sun. During a galactic collision, the increased frequency of distant stellar passages could disturb these outer solar system objects, potentially sending some comets toward the inner planets. However, such events would likely represent only a modest increase over the background rate of comet showers that planets already experience over geological timescales. Another potential hazard comes from regions of enhanced star formation triggered by galactic collisions. When galaxies merge, the compression of gas clouds can create starburst regions where new stars form at rates hundreds of times higher than normal. Many of these new stars are massive, hot, and short-lived, ending their brief lives as supernova explosions that flood their surroundings with intense radiation. A planetary system passing near these active star-forming regions might experience elevated radiation levels that could potentially affect planetary atmospheres and surface conditions. However, even this risk must be considered in proper context. The vast majority of stars in merging galaxies remain far from the most intense starburst regions, and the timescales of dangerous exposure would likely be relatively brief compared to the billions of years over which complex life evolves. Most planetary systems would probably pass through any dangerous regions quickly enough to avoid permanent sterilization, though they might experience periodic challenges to their biospheres that could drive evolutionary adaptation. For our own solar system's future during the Milky Way Andromeda collision, the timing presents an interesting alignment of cosmic events. The merger is expected to begin in about 4 billion years. roughly the same time frame in which our Sun will exhaust its hydrogen fuel and begin to expand into a red giant. As the Sun swells, it will likely engulf Mercury and Venus and render Earth uninhabitable through intense heating. This stellar evolution poses a far more direct and certain threat to life on Earth than any effects from the galactic collision occurring simultaneously. The coincidental timing of these events, our star's life cycle and our galaxy's merger, offers a cosmic perspective on the multiple scales of change affecting any planetary system. While we often focus on threats from asteroids, supervolcanoes, or human activity that operate on timescales of years to millennia, the ultimate fate of Earth is tied to processes unfolding over billions of years, involving both stellar evolution and galactic dynamics. Perhaps counterintuitively, galactic collisions might actually increase the potential for life in the universe through several mechanisms. First, the enhanced star formation triggered by these mergers creates more solar systems, increasing the statistical opportunities for life-bearing planets to emerge. Second, the distribution of heavy elements, carbon, oxygen, nitrogen, and other ingredients essential for life as we know it, is accelerated during merger-induced starbursts, enriching the galactic environment with the chemical building blocks of potential biospheres. The redistribution of stars during mergers could also bring planetary systems into new galactic environments with different radiation backgrounds, interstellar medium densities, and neighboring stellar populations. These changing conditions might occasionally benefit existing biospheres or create new opportunities for life to emerge on previously inhospitable worlds. Like ecological succession following disturbance in terrestrial ecosystems, cosmic disturbances may create new niches and opportunities across galactic scales. An intriguing possibility is that galactic mergers might even facilitate the spread of life between planetary systems if it exists in multiple locations. The concept of panspermia, the hypothesis that life can spread from one world to another via meteoroids or other space-traveling objects, becomes more plausible when stars are brought closer together during galactic restructuring. If life-bearing material can survive interstellar transit, reduced distances between stars during certain phases of galaxy mergers could increase the probability of successful transfers. For any advanced civilizations that might exist during galactic collisions, these events would unfold so gradually that they would have countless generations to adapt their technologies and strategies to any changing conditions. An interesting speculation is that sufficiently advanced civilizations might even take advantage of the gravitational dynamics of merging galaxies to facilitate interstellar travel, using the shifting gravitational landscape to assist in the tremendous energy requirements of journeying between stars. From an astrobiological perspective, the most significant impact of galactic mergers may be their influence on the long-term habitability of galaxies as integrated systems. The transformation of gas-rich, star-forming spiral galaxies into gas-poor ellipticals through major mergers gradually reduces the overall star formation rate in the universe. This decline in cosmic star formation, observed by astronomers over the past 10 billion years, represents a slow transition from a universe optimized for stellar birth to one increasingly dominated by aging stellar populations. Since habitable planets require relatively young stars with stable energy output, this transition suggests that the universe's capacity for hosting life may already have peaked, with the potential for new biospheres gradually declining as galaxy mergers reduce the gas reservoirs available for forming new stars. The elliptical galaxies that result from major mergers might be thought of as cosmic retirement communities, architecturally elegant but with diminished generative potential compared to their spiral predecessors. Yet even elliptical galaxies continue to the mice, the whirlpool, and other interacting systems are frozen moments in a drama that extends far beyond human timescales. Yet through astronomy, we can piece together these moments to comprehend the full narrative arc of galactic evolution. The ultimate lesson from studying life's prospects during galactic collisions might be one of cosmic perspective, a reminder of how processes unfolding on vastly different scales can coexist with minimal interference. While galaxies collide and transform over billions of years, life on planetary surfaces can continue to evolve around steady stellar hearths, largely insulated from the grand restructuring taking place across thousands of light years. This nested hierarchy of stability within change characterizes our universe across multiple scales. This perspective also highlights the remarkable hospitality of our cosmos despite its violent aspects. The same forces that drive galaxy collisions, gravity, and the conservation of angular momentum also create the stable planetary orbits that allow life to flourish on worlds like Earth. What appears catastrophic at one scale enables existence at another, revealing a universe that, while not designed for life, contains fundamental properties that make life possible even amid cosmic upheaval. As we contemplate humanity's place within this grand cosmic context, galaxy collisions remind us of both our vulnerability and our remarkable good fortune. We exist in a universe where change is constant, yet unfolds at scales that allow complex structures like galaxies, stars, planets, and ultimately living things to develop and persist. The collision of galaxies, far from representing cosmic catastrophe, embodies the creative restructuring that has made our existence possible and will continue to reshape the universe long after our sun has exhausted its nuclear fuel. With every galactic collision, the universe continues its grand cycle of creation and transformation, building ever more complex structures from the gravitational dance of its components. This ongoing process, neither entirely chaotic nor rigidly deterministic, continues to unfold across cosmic time, writing new chapters in the universe's autobiography through the graceful violence of merging galaxies. As we gaze into the depths of space with our most powerful telescopes, we're not just looking outward, but also backward in time. The light from distant galaxies has traveled for billions of years to reach us, showing the universe as it appeared in the remote past. This cosmic time machine allows astronomers to observe how galaxy collisions have evolved throughout cosmic history and project what lies ahead for these spectacular events. The most dramatic change in galaxy collisions has been their frequency. When we observe galaxies from over 10 billion years ago, we see a universe teeming with collisions and mergers. Galaxies were closer together in the younger, smaller universe, and their relative velocities were often lower, making gravitational captures more likely. In this early epoch, major galaxy mergers occurred up to 10 times more frequently than today. This elevated collision rate helped build up the large galaxies we now observe, as smaller systems merged into increasingly massive ones. As the universe expanded, the average distance between galaxies increased, and the cosmic collision rate gradually declined. Today, in our cosmic neighborhood, major mergers are relatively rare events, though minor mergers, where a large galaxy absorbs a much smaller companion, remain common. This declining collision rate represents a fundamental transition in cosmic evolution, from a young universe dominated by violent assembly to a more mature cosmos where existing structures evolve more gradually. The future of galactic collisions is intimately tied to the ultimate fate of the universe itself. The discovery in 1998 that the universe's expansion is actually accelerating, attributed to a mysterious force called dark energy, dramatically changed our understanding of cosmic destiny. This acceleration means that galaxies not already bound together by gravity will drift ever further apart as space itself stretches between them. Over incredibly long timescales, this expansion will isolate galaxy clusters from one another, creating island universes that can never again interact. In our own cosmic neighborhood, the most anticipated collision is between the Milky Way and Andromeda galaxies, currently approaching each other at about 110 kilometers per second. Precise measurements have allowed astronomers to predict that the first close encounter between these spiral giants will occur in approximately 4.5 billion years. This cosmic rendezvous will set in motion a gravitational dance lasting billions of years, with multiple close approaches before the galaxies finally merge completely. Computer simulations of this future merger, often nicknamed Milkomeda, provide a preview of the cosmic restructuring awaiting our galactic home. During the first close pass, the galaxies will distort each other gravitationally, drawing out long tidal tails of stars and gas. The second encounter, a few billion years later, will be more disruptive, throwing stars into chaotic new orbits and triggering massive bursts of star formation. After several more approaches, the galaxies will merge completely, likely forming a giant elliptical galaxy that bears little resemblance to either of its spiral progenitors. What would the night sky look like to any observers still present on Earth as this merger unfolds? As Andromeda approaches, it would gradually grow larger in our night sky, eventually spanning several times the width of the full moon and displaying its spiral structure to naked-eye observers. During close passes, the combined gravitational forces would create spectacular arcs and streams of stars visible as glowing bands across the heavens. The merger would transform our familiar night sky into a cosmic light show unlike anything in recorded human experience. Of course, by the time this galactic merger occurs, the Earth itself may be uninhabitable due to the Sun's evolution into a red giant. But if humanity or its descendants somehow survive, they would witness one of the most spectacular transformations possible, the complete restructuring of our cosmic neighborhood through the gravitational ballet of galactic collision. Beyond our local group, similar mergers will unfold within other bound galaxy clusters. The Virgo cluster, containing about 1,500 galaxies, will continue to interact and merge over billions of years. But between these bound clusters, cosmic acceleration will eventually make further interactions impossible. After about 100 billion years, galaxies outside our local group will recede beyond our cosmic horizon, becoming permanently unreachable and eventually unobservable, even with the most powerful theoretical telescopes. This accelerating expansion creates a cosmic deadline for intergalactic travel. If humanity or any other technological civilization ever hopes to explore beyond our local group, it would need to develop interstellar travel capabilities within this 100 billion year window. After that, the accelerating expansion will make journeys to other galaxy clusters physically impossible, no matter how advanced the technology. As we project even further into the deep future, trillions of years ahead, the universe will become increasingly isolated and quiescent. Within each island universe formed from merged galaxy clusters, stars will gradually exhaust their nuclear fuel and fade away. The lowest mass stars, red dwarfs, can shine for up to 10 trillion years, but eventually even these stellar embers will flicker out, leaving behind white dwarfs, neutron stars, and black holes as the only remnants of once vibrant galaxies. In this far future universe, traditional galaxy collisions will no longer occur. Instead, the remaining compact objects will occasionally interact through gravitational encounters. Over incomprehensibly long timescales, many of these dense objects will be flung out of their host galaxies entirely, while others will spiral toward the central supermassive black holes, building up these cosmic leviathans at the expense of the surrounding stellar population. The final major collisions in cosmic history won't involve galaxies as we know them, but rather the supermassive black holes that once sat at their centers. As these behemoths gradually absorb matter and occasionally merge with other black holes, they will grow increasingly dominant in the aging universe. In the most extreme future scenarios, each bound cluster might eventually be reduced to a single enormous black hole, containing most of the mass that was once distributed among billions of stars. For astronomers studying galactic collisions, this perspective provides context for our observations. When we observe distant galaxies caught in spectacular mergers, we're seeing snapshots from a grander cosmic narrative. The story of how gravity has shaped and continues to shape our universe across timescales that dwarf human experience. The tools we use to study these processes continue to evolve, allowing increasingly detailed views of galactic interactions. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can peer through cosmic dust to reveal collisions hidden from optical telescopes. Future observatories, both ground-based and spaceborne, will provide even sharper views, while gravitational wave detectors will allow us to hear the mergers of supermassive black holes that often conclude the galaxy collision process. As we continue to explore the past, present, and future of galactic collisions, we gain perspective on our place in cosmic time, a moment when collisions are still occurring, but less frequently than in the universe's youth, a time when our local cosmic neighborhood remains dynamic before the accelerating expansion eventually isolates it forever. Every collision is a testament to the universe's endless motion, a story of destruction and creation written across the stars. From the violent mergers of the early universe to the slow-motion dance of the Milky Way and Andromeda that will unfold over billions of years to come, galactic collisions represent both endings and beginnings in the ongoing narrative of a universe in perpetual transformation.